This is for Math 1325, Business Calculus. We're going to be jumping into the first section that we cover, which is section 2.1. One thing that can help each time you're doing each new section is to open up the electronic textbook and maybe skim through anything that's, whenever they have it in a colored box like this, that's usually some rule to know or a definition or some formula. Here it's just describing what a function is about. Domain and range is common from even back in algebra of high school. They have many examples too that you could possibly look at. Here's another example showing domain and range. Example 3, here's agreement on domains. Example 4. Example 5. This early part of chapter 2 is reviewing some algebra concepts actually. Vertical line test, this is a way to check if a graph is a graph of a function or not. Even and odd functions. So not a lot of rules to know here, but at least there's all those pages you can skim through as needed. So I'm going to close that and come in here, Math 1325, Fall 2022. So you get to the ebook by hitting e-text contents. Choose a chapter like chapter 2 and choose a section like 2.1, and then you can view the e-text, or you can even watch a video presentation of it if you want. Then I can go back to the main menu. Assignments, this is where you do all your coursework. So all homework, reviews, and tests will be here eventually. This semester, since they switched to the 8th edition, I mentioned how I'm going to have to build everything from scratch all over again. But 2.1 is here, and there are 20 questions. I got one wrong on purpose last time just to show you how the system works in here. But it doesn't matter. As long as I get them all done by September 23rd when they're due, then it doesn't matter if I get them wrong at first. Okay, determine whether the correspondence is a function. So anytime you have two things related to each other, one's called the domain, the other one's called the range. Usually the domain comes first. Domain are things that you plug in to, say, equations or graphs, and then the range is what spits out as an answer in essence. And when you have two things related like that, that's just called a relation. A function is a special relation that none of the domain values can repeat. So there's different ways to represent this. One is these little charts or bubbles where they list all the domain below one and all the range below the other, and then they can have arrows pointing to them. Each arrow is a coordinate, basically. So there's the coordinate 1620, 1421, and 1820. You don't have to write these down, but if you did write them down, 1620, 1620, that's a coordinate. 1421, and 1820 was the last one. If you can write every coordinate down like we can here, then you can look, the first part of each coordinate is the domain. All three of those are different, 16, 14, 18. This is a function. A function just has the requirement that the x's cannot repeat, the domain cannot repeat. You can't have a 1620 and a 1621, otherwise you got two 16s going with different numbers. So it doesn't matter what happens in the range. It actually turns out the range is repeating, but that's okay. The range can do whatever it wants to do. Only the domain is not allowed to repeat. So yes, this is a function. In fact, if you have a problem like this, all you have to make sure is that each arrow leaving is only once leaving. There's only one arrow leaving 16, there's one arrow leaving 14, there's one arrow leaving 18. It doesn't matter that there's two arrows coming to 20. In fact, looking over here doesn't even determine the answer at all. So if there was an arrow leaving 16 going to 20, and then another arrow leaving 16 and going to 21, two arrows leaving 16, that would not be a function. Okay, once you have a function, then they will write function notation. G of x is the way this is read. G of x equals 1 over 4 minus 9x. If the notation f of x or g of x is already there, then you don't have to determine if it is a function or not. It's automatically a function if they're using that notation. G of x 1 over 4 minus 9x. There are a handful of things that can make a domain have an issue. One is anything that makes a denominator of a fraction equals 0. So if I set the denominator equal to 0, I can find all the x values that make it equal 0, whether there's 1 or 2 or 20 or none. So this is a linear equation. It's only going to have one solution. So therefore, there's only one number that causes an issue in the domain. And that it doesn't matter if it comes out nicely. This one's not going to come out nicely, but that's okay. Divide by -9. 4/9. Two negatives in division is a positive. 4/9. This is the only number that would cause the denominator to be 0, and that would make the whole fraction undefined. So the domain is all real numbers except for this. And there's different ways you could write that. You could literally just, in a phrase, say all real numbers except 4/9. Sometimes they do an interval notation, which you would write -infinity until you get to 4/9. Parenthesis means do not include it. Union, and then you do another do not include 4/9 and go all the way to infinity. So this would be a domain. The domain, this is a way to say everything except 4/9 in interval notation. Now, one issue with doing all your work in MyMathLab is you have to know what kind of format they want. And if it's this one's multiple choice, but if it's free response, if you don't give the format they're looking for, they can sometimes count it wrong, even if it's equivalent to it. But they're writing, this is a set notation where you put squiggly. I want the set of all x such that x is a real number and x cannot equal something or has to be greater than or equal to something. Well, the rule is it can't equal 4/9. So this would be another way to say all real numbers except 4/9. If you look for the domain of a square root, that has to be greater than or equal to 0. So that's probably why they had choice C as a greater than or equal to. Here's the same thing, except the denominator has a square in it. So now you can actually get two numbers that make the denominator 0. G of x is x over x squared plus 8x plus 12. We don't care if the numerator is 0. 0 divided by something is 0. That's in the domain. The domain is what number can you plug in so that you get some kind of answer spit out. You'll get an answer unless the answer is undefined. So the only thing that causes undefined answers in fractions is when the denominator equals 0. So if I set the denominator equal to 0, I don't have to worry about the numerator. Then we could factor this and get two different values that make the denominator 0. This is factoring a trinomial. When I factor a trinomial, I look at the last sign. If that's plus, then your answers have both of these. Both answers are positive. If this had been a negative, then I would have got two negatives. If this is negative, then you automatically get one positive and one negative. I need two numbers that multiply to 12 and add to 8. And that would be 6 and 2. 6 times 2 is 12. 6 plus 2 is 8. It meets both conditions. So then I have a product equal to 0. That can only happen if at least one of these is 0. The only way you can multiply two things together and get 0 for an answer is if at least one of them is 0. And then you just solve each equation. X equals -6. X equals -2. -6 and -2, they're the only two numbers that would make this denominator 0. And they're the only two numbers I need to exclude from my domain, because otherwise they'll cause the answer to be undefined. There won't be an answer. So if I was doing interval notation, it would be -infinity to -6, or -6 to -2, or -2 to infinity. That's a way to exclude two different numbers in interval notation. But notice that gets kind of long and cumbersome. So it's sometimes easier just to do it in a phrase like this, or just even in symbol form. We want all x such that x cannot equal -2 or -6. Both of those have to be excluded. So with denominator, with fractions, you want to know what makes the denominator 0. In square roots, it's what makes the inside of the square root greater than or equal to 0. So I have a square root of 9 minus x. You can't do square roots of negatives unless you're going to use imaginary numbers. And even that is just kind of made up answers, so they're not really part of the domain. So I take the inside of the radical and set it to greater than or equal to 0. These are the ones that are good, actually. So I can subtract 9. -x is greater than or equal to -9. Then I have to get positive x, so I'm going to divide by -1. Anytime in an inequality you divide by a negative, you flip the inequality. -9 divided by -1 is 9. So this is the domain. This is what's good. X's have to be less than or equal to 9, and then I'm going to get an answer. If I plug 9 in right there, 9 minus 9 is 0. The square root of 0 is 0. If I plug in, say, 8, 8's less than 9. 9 minus 8 is 1. The square root of 1 is 1. If I plugged in 5, 9 minus 5 is 4. The square root of 4 is 2. Any number that's 9 or less, if I plug it in, I can get some kind of answer. But if I plug in anything bigger than 9, like 10, 9 minus 10 is -1. The square root of -1 is imaginary. So it's not technically an answer to the problem, and therefore it's not in the range. There is no range answer as a problem. So we need less than or equal to 9. This is an inequality way of writing it. The interval notation would be -infinity to 9 with a bracket because of the equal to. This is the interval notation way of saying less than 9, less than or equal to 9. So that's B. Okay, this is similar to the first problem. I have each one of these vertically as a coordinate. There's a coordinate for 9, 3, 4, 2, 1, 1, 0, 0, 1, -1, 4, -2, and 9, -3. There's 7 different coordinates. But there's a 9, 3, and a 9, -3. The 9s are repeating. The 4s repeat. The 1s repeat. This is not a function. All you need is 1 repeat, and you would say no, and we have 3 repeats. So I could have stopped after I noticed that there was a 1, 1, and a 1, -1. Okay, for equations, probably the best way to handle this is to draw a graph. And maybe you're familiar with this graph. An absolute value graph. In algebra, they teach students to do what's called a parent function, or a basic function of it. This is the parent function for absolute value of x. And then when there's a 4 multiplied inside, that's a horizontal shrinking. If the 4 was on the outside, it would be a vertical stretching, and all the y coordinates would get multiplied by 4. And actually, it turns out a vertical stretching of 4 is similar to a horizontal shrinking of 4. So, but this is what happens here is instead of multiplying by 4, you end up doing the opposite and you divide x's by 4. So say you had the coordinate 4, 4 right here. I'm picking that because of the 4 right here. You would divide the x by 4. And the 4, 4 would turn into 1, 4, which would be like right there. So we'd make it really narrow, and it would have the same effect as a vertical stretching times 4. A vertical stretching times 4 is just like a horizontal shrinking divided by 4. Because whether you move in this way by a factor of 4, or if you go up this way by 4, if you multiply this by 4, you'll land on the line too. So this wasn't the one we had, but just in case you get that, then you know how to handle it. But the point is, it's a real thin absolute value shape. This would be a function because it passes the vertical line test. But the problem I actually had was reversed. It was written this way: x equals the absolute value of 4y. X equals the absolute value of 4y. Well, the only difference when you switch the x and the y is, on the parent function anyway, it looks like this instead. And then again, if you narrow the y's, you'll end up getting thinner like this. In either case, this is going to fail the vertical line test. So there could be two different x's for the same y. If I plug in a y of 1, 4 times 1 is 4, absolute value of 4 is 4, the x would equal 4 if y is 1. But if I plug negative 1 in for y, negative 1 times 4 is 4, but the absolute value of negative 4 is positive 4. So x equals 4 even when y is negative 1. So I have a repeat of the x's for two different y's. That's not a function. So the rule does not define y as a function of x. It's either a or d. It's definitely not b or c. The rule assigns every x value more than one y. The rule assigns some x values more than one y. See, this would be hard to know if you didn't know what the graph looked like. But the first one's true except for right at the corner point right here. 0, 0 only happens once. And this is kind of extra information to know, because you normally don't need to know if there's more than one or all of them. The rule assigns every x value more than one or some. That doesn't really matter in terms of whether you say yes or no to a function normally. All you need is one spot where there's more than one y value for a given x. And if it's every x or some x's or even just one x, all of those are still no. I guess the only point of this is they're trying to see if you thought every x has it a repeat. It does, except for 0, 0 is the one time it doesn't. So really, even the sum is a little misleading because it's every x except for 0. Okay, so now if I get something like y equals 2x plus 4, that's a diagonal line. If you remember that from algebra, y equals 2x plus 4. That's a line with a y-intercept of 4 and a slope of up 2 over 1. So you get this diagonal line. It's going to pass the vertical line test. This is a function. So I can plug in given x values. They're giving me the domain or the x values. They want me to find all the y's for those. So plug negative 2 in. 2 times negative 2 is negative 4 plus 4 is 0. Now it does say type ordered pair, so I guess they want, when I plug negative 2 in, I get an answer of 0. Then I'm going to plug negative 1 in. Negative 1 times 2 is negative 2, plus 4 is 2. Then we're going to plug in 0. That's a nice one because then the answer is just 4. Plug in 1. 2 times 1 is 2, plus 4 is 6. Plug in 2. 2 times 2 is 4. 4 plus 4 is 8. And finally plug in 3. 2 times 3 is 6. 6 plus 4 is 10. So notice I plugged in 1, 2, 3, 4, 5, 6 different x values. None of them repeated. And I got 6 coordinates. Then they want me to graph each one of these. Okay, -2, 0 is 2 to the left of the origin. -1, 2 is 1 to the left, up 2. 0, 4 is up 4. See how they're lining up? 1, 6, 1 to the right, up 6. These were the 2 points I graphed on my sketch, 0, 4 and 1, 6. 2, 8 is over 2, up 8. Oops. And over 3, up 10. So the range, so the domain was given -2, -1, 0, 1, 2, 3. The range is 0, 2, 4, 6, 8, and 10. And you typically will write this in order from lowest to highest. If there's repeats in the range, that's okay. We didn't get any repeats, but if you get them, that's normally okay. And then you don't normally write the repeats in here when they ask you to list the range. Now, even though the equation y equals 2x plus 4 is a straight line forever, if they give me a limited domain, then I can have a limited range and just have these points. It's not necessarily the whole line. Same deal here. Okay, so we're going to plug in 0 through 5 for all the x's. Oops, didn't get the parenthesis on that one. There, whoops. There. So I'm just putting them all the given domains first. There, 0 through 5. Plug in 0, you'll get 0 times 0 plus 1. You would do the parenthesis first. 0 plus 1 is 0, is 1. 1 times 0 is 0. So this limited domain would give me one coordinate of 0, 0. Plug in a 1. The 1 plus 1 would be 2 times 1. 2 times 1 is 2. Plug in 2. The parenthesis would be 2 plus 1, 3. 3 times 2 is 6. Plug in 3. 3 plus 1 is 4. 4 times 3 is 12. Then you're going to get 4 times 5, which is 20. And finally, 5 times 6, which is 30. Now, this is not forming a line, even if I did more points than this. 0, 0 is all done, so just check answer. 1, 2 is over 1, up 2. But then we go over 2, up 6. So it's not linear. It went up 2 over 1, but now it's up 4 over 1. 312. 312's way up here. 420. Oops, moved it. The mouse is real sensitive. You got to watch out for that. You can be where you think you are and let it go and it moves on you. And then 530. This is actually part of a parabola, because if you distributed this x, you'd get x squared plus x, which is quadratic. So the range were these 6 answers: 0, 2, 6, 12, 20, and 30. There's no repeats, they're already in order. 0, 2, 6, 12, 20, and 30. Okay, here's another domain. So this is similar to one we had earlier. If you have a square root, the domain is everything except whatever makes the inside of the radical negative. So what I do is I set it equal to, greater than, or equal to 0. That's all the good stuff. It can be bigger than 0, it can be equal to 0. Only when it's less than 0 is there an issue. Then you get imaginary answers. So if I subtract 4, divide by -1, divided by negative, I got to flip the inequality, and then do the square root. So we get a little bit of an issue here with the less than or equal to plus or minus 2. That doesn't make a whole lot of sense when you do it that way. So let me go back at this point. Right when I had this point here, instead of taking the square root, what if I move the 4 back over and factor it into a difference of squares? X plus 2 and x minus 2. So you get 2 spots that make it equal 0 exactly. Both -2 and +2 are good answers because you can equal 0. But what I would want to know is, what would make this stuff less than 0 is what we really want to know. And that's stuff that's in the domain. So what you do is you make a number line from -2 to 2. We already know these spots are good. -2 and 2 are both good. And then I'm going to do test points. I'm going to try -3, 0, and 3. And plug them into, you can plug them in here or here. Usually the factored parts are easier, and you want to see if they're less than 0. If they're less than 0 or negative, those are good regions. So the easiest one is 0 first. If you plug 0 in here and there, you'll end up with +2 times -2. That's -4. So everything between -2 and +2 is a good region, including those numbers. So that would be like a bracket here and a bracket there. If I plug 3 in, 3 minus 2 is 1, 3 plus 2 is 5, 5 times 1 is 5, that's greater than 0. So this region's no good. And -3 would give me -3 plus 2 is -1, -3 minus 2 is -5, -1 times -5 is also +5, that's no good. So only between -2 and 2, including both of them, those are the only numbers you can plug in. If I plug a 1 in, let's say, 1 squared is 1, 4 minus 1 is 3, the square root of 3 has an answer, it's like about 1.7. But if you plug in 5, let's say, 5's not between -2 and 2, 5 squared is 25, 4 minus 25 is -21, the square root of -21 is imaginary. So another thing too about a problem like this is if you set this equal to y, if you were to square both sides of this equation, you would get y squared equals 4 minus x squared, because the square would cancel the square root out. You could then move the x squared over to the other side. This is the equation of a circle. We learned this in algebra 2. This is a circle with a 0, 0 center, and the radius is the square root of 4, which would be 2. A circle with a radius of 2 this does have a domain from -2 all the way to +2. And it hits those spots exactly too. The farthest to the left I can go is -2. The farthest to the right I can go is +2. So that confirms that the answer is between -2 and 2. Answer your answer in interval notation, but I do need bracket, -2, 2 bracket. And they don't have a bracket in this toolbar. You just have to hit it on a keyboard somehow. Keyboards have a bracket. Sometimes in math you can do that, where you can do a problem more than one way and either confirm the answer or just do it the easier way every time. Okay, give the domain and range, then use the graph. Okay, so domain is how far left and right you can go. The farthest to the left I can go is -4 on the x-axis. And it does have a closed circle there, so it touches that spot. Bracket -4. The farthest to the right I can go is right here, which is an x value of 2. So the x's are always between -4 and +2. The range, you want to go down to up. The lowest down you can go is either there or there. Those both have y values of 0. Range is about the y's. 0, and the highest one I can reach is there or there, but both of those are a y value of 4. So the range is 0 to 4. F of -2. So this means find y when x is -2. When x is -2, I'm right there. That has a y value of 0. This is what domain and range are all about. If I plug -2 in from the domain, I get 0 from the range. F of 0, when x is 0, I would have to go right here to touch the graph. This has a y value of 4. F of a half, we're going to have to estimate this. A half would be here for the x. 1, 2, maybe 3. What values of x for which f of x equals 2? If f of x equals 2, that means the y is 2. You want to find the x's when the y is 2. Y being 2 is right here. There's an x that does it there, there's another one there, and there's even another one there. So when x is -3, or if x is -1, or if x is +1, all three of those x's produce a y of 2. And remember, the y's can repeat. So I can have a -3, 2. I'm not going to put coordinates, but if I did -3, 2, -1, 2, and +1, 2, all three of those have different x's. So the x's are not repeating. This is still a function. It passes the vertical line test. Okay, this is the one I got wrong on purpose last time. Okay, so... well, they did the first part. I got this wrong because I just put phony answers in, but notice it's just like the last problem. The farthest to the left you can travel on this little windy segment is right there. There's the farthest to the left. X is -2. The farthest to the right is when x is 5. And close circles, so then you do touch them exactly, so brackets. The lowest down you can go is here, and that's a y value of -3. The highest up you can go is there, which is a y value of 2. Now find f of -2. That means when x is -2, what does y equal? It equals -3 down there. F of 0, when x is 0, you'd have to go down here and touch the graph. That's exactly a -1 y value. F of 1, when you're here for 1 for x, it looks like it's maybe a half. It doesn't say fractions or decimals. Maybe they would take either one then, 0.5. Oh, no, it's negative is why I did that wrong. It's -0.5. There it goes, okay. And then find all the x's so that f of x is 1. In other words, when y is 1, what do the x's equal? When y is 1 right here, there's nothing over here. And going this way, there's only that one spot right there. So maybe 3.5 or 3.5. So it's not that you have to get multiple answers of that. Okay, so this is just function notation. They give me f of x equals 4x squared minus 44x plus 121. Find the value of f of 4. That just tells the reader plug 4 in for any x. So we need to do 4 times 4 squared minus 44 times 4 plus 121. Here's where if you have a graphing calculator, it could help. You don't have to have one, but with a graphing calculator, I can type that in all at once. I'll type it first and then show it to you closer. So I put 4 parenthesis, I'm going to plug in 4, close parenthesis, squared, minus 44 parenthesis 4, parenthesis plus 121. So this way, in parentheses, I put the parts that I'm plugging in the 4. And otherwise, it looks just like the equation did. Press equals, and the answer is 9. If you only have to do this once, then that's fine. Just do it slower if you don't have a graphing calculator. But if you get problems like this where there's a part A, B, C, D, E, it kind of gets boring doing that a bunch of times. So now what I can do to quickly do negative 1/2 is, well, I guess it'd just be easy to retype it again. So 4 parenthesis negative 1 divided by 2 parenthesis squared minus 44 parenthesis negative 1 divided by 2 parenthesis plus 121. So I did it the same way. I just put negative 1/2 in instead of 4s. And the answer coincidentally was 144. If you're plugging an A in, then you don't need a calculator. You just literally replace any x with an a. So 4a squared minus 44a plus 121. And if you have 2 over m, I guess we should work this one out. So the function's 4x squared minus 44x plus 121. And we're trying to do f of 2 over m. So first put the 2 over m everywhere there's an x. The parts that have variables are going to get stuck there, but the one issue is 2 squared is 4. And then you get m squared in the denominator. So this will be 4 times 4 over m squared. And then the rest is just like it is. So if this 4 was in the denominator, it could cancel that 4, but they're both in the numerator, so that's 16 over m squared. And same deal here, you can multiply these and get 88 over m plus 121. Oftentimes on these problems where there's variables involved, you don't really care how messy the answer looks. It's almost like a formula that you're creating. And then if you give me a value of m, I can plug it in down here, and I could do that for multiple different m's, and then this is a matter of plugging it in. So 16 over m squared minus 88 over m plus 121. Find the values of x such that f of x equals 1. So that's putting a 1 over here. Put a 1 where the f of x is. So you get 1 equals 4x squared minus 44x plus 121. And then you're basically solving this equation like an algebra. So I would minus 1 to get it equal to 0. And this will help because all these numbers divide by 4 now. It's always best in solving quadratics if you can have a 1x squared rather than a 4x squared or any other number besides 1. You can't always do this, but when you can, it definitely helps. Divide everything by 4. And this is also why we like it equal to 0, because 0 divided by anything is still 0. That makes 1x squared minus 11x and plus 30. So now we're going to factor a trinomial again. Again, there's a plus in the back, but this time there's a negative in the front, so then we get 2 negatives. Got to multiply to 30. That could be 1 and 30, 2 and 15, or the most common one is 5 and 6. And you're trying to add to this 11, so yeah, that makes sense. 5 and 6 adds to 11. And it's definitely both negatives, because negative 5 times negative 6 is how you get positive 30 when you multiply. Negative 5 plus negative 6 is how you get negative 11 when you're adding. And anytime you have 1x's here, the answer is just switch to the opposite. So x equals 5 and x equals 6. So there's 2 different x's that make the y equal 1 in this function. And that's fine because the y's can repeat. We don't care about that. 5 and 6 are the 2 x's that make that happen. So this is a business calculus class, but even in regular calculus, the hardest part to calculus is all the algebra that it's filled with. So we're going to see a lot of that here too in business calculus too. For piecewise functions, when they ask you to do f of 2, you plug that into only one piece or another, never more than one. And only if x equals 2 exactly, the answer is just automatically 6, is what that means. If x is not 2, then you have to take whatever it is and plug it in. So for part A, since it was f of 2, the answer is just automatically 6. Since I don't have 2 here, then I need to plug this negative 1/2 into both of these x's right here. So the function is 2x plus 3 over x minus 2. And unless you're doing 2, if you're doing any number other than 2, this is what you plug it into. So 2 times negative 1/2 plus 3. And then negative 1/2 minus 2. So this is going to be messy with fractions inside of fractions. But at least this part comes out nicely. 2 times negative 1/2 is negative 1. The top of the fraction is 2. Unfortunately, in the bottom, you'd have to get common denominators. This part here alone would be 4 over 2. So negative 1/2 minus 4 over 2 is negative 5 over 2. So I have a fraction inside of a fraction. 2 over 1 divided by negative 5 over 2. There's a little phrase I tell my algebra classes when they get a situation like this. It's nice because it's kind of like a little poem that they can remember better. This is kind of a junior high thing, but even calculus students find this useful. When dividing fractions, that's what we're doing literally right here, is I have 2 fractions divided by each other. And even if one of them is not a fraction, you can just put it over 1. When dividing fractions, don't be shy. Flip the second and multiply, because it rhymes like a poem. When dividing fractions, don't be shy. Flip the second and multiply. It's hard to divide fractions. But if you flip the second fraction, flip is a reciprocal. If you flip the second fraction, in the denominator alone, the 5 cancels the 5, the 2 cancels the 2, and even the negative times the negative is positive. It gets rid of the entire denominator. So now you don't have a fraction divided by fraction, you have a fraction times a fraction. That's easier to do. In fact, that's the easiest thing to do of all with fractions, is to multiply them. Adding fractions is hard, but multiplying is easy. So you go straight across. 2 times -2 is -4. 1 times 5 is 5. The answer is -4/5. So this only got hard because we had fractions inside of fractions. Now, especially because you're going to be taking your tests in MyMathLab, you got to read. I fall victim to this too myself. Type an integer or a simplified fraction. If you don't do that, they count it wrong even if your answer is equivalent. Remember before when I had a -1/2 answer and I wasn't sure if they would take a fraction or a decimal? If they don't mention it, then that's when they'll take either one. But if they mention it specifically and you don't do that, they count it wrong even if your answer is equivalent. So if I were to put -0.8 here, they would count it wrong because they didn't ask for a decimal, even though -0.8 is equivalent to that. Okay, f of a, well, I guess a could be either one. So if a happens to be 2, the answer is automatically 6, so that's easy. And if a's not 2, then you're just going to plug a's where these x's are. So that's easy too. You just, instead of x's, put a's. 2a plus 3 over a minus 2. So that's an easy one. 2 over m is going to be harder. If m equals, that's weird. Okay, if m is 1, would that make... Oh, see, yeah, that's right. See, if m equals 1, then you really do have 2 over 1. That's when you would have 2. So if m equals 1 is the same thing as saying that x would equal 2. So that answer is automatically 6. And then if it's not 2, then you have to plug it in the first one and put a 2 over m where these x's are. Now, one issue is, will they take fractions inside of fractions? So if I put 2 over m right there, that this 2 will multiply by that 2 and make 4 over m. And then you'd have your plus 3 just from the top of the fraction. And then you want to put a 2 over m right where that x is. Minus 2. I don't know if they're going to not accept this answer because sometimes they don't like fractions inside of fractions for a final answer. If they don't take this answer, I'm going to show you a nice shortcut that you can do to finish it. But if they will take it, I don't want to waste time doing that. Okay, they took that. So it was literally all about just plugging the 2 over m in. And then if y is going to equal 1, well, it's not going to be this one then, because this is when y equals 6. So anytime x is 2, the y is 6. If the y is not 6, then you're not going to get this 2 for an answer. Otherwise, it wouldn't be a function. So this is 1. That's the y. So all I have to do is set this fraction equal to 1. 2x plus 3 over x minus 2. That has to equal 1. And I could make this 1 over 1 and cross multiply. I now have a proportion from geometry, a fraction equal to a fraction's proportion, and you can cross multiply that. And luckily 1 times anything is the anything, so I just get the 2 halves of the fraction equal to each other. Now solve for x. 2x minus 1x is x. Subtract 3. X would be -5. So apparently there's only one x value that would make the y value 1. If I plug a 5 in, I would get 10 plus 3, 13. Although that doesn't seem to make sense. Over, oh no, -5. Yeah, see, that didn't make sense. Good thing I was double checking it. See, -5 times 2 is -10. Plus 3 is -7. And the bottom would be -5 minus 2, which is -7. -7 divided by -7 is 1. So only -5, that's the only one that can make the y value equal 1. Okay, we're going to see this often in Chapter 3, is why they're kind of preluding this here. We're on number 14. I have a quadratic function. G of x is x squared minus 4x plus 3. One of the three big concepts in calculus involves this, actually. This is the algebra side of it, though. The calculus side to this is very easy, but the algebra side is complicated. But they teach this even in a college algebra class, this one problem right here. So I want to find g of r plus h. Algebra students always find this confusing, like, why do you want to throw all these weird variables in here? But all it does is it takes the place of that x the same way those m's did before those a's. So everywhere you see an x, you just put r plus h. You don't care how messy it looks. The x squared, the x becomes r plus h, and then it's still squared. The minus 4 is still there, and then you put an r plus h in that x plus 3. This is one of the steps we do when we're doing one of the three big concepts in calculus. When we get to that, I'll remind you of this at that point. Now, r plus h squared, you're going to do this a lot in that next chapter. So the shortcut is you do the first one squared. You multiply this together and double it. R times h is literally RH, but then it gets doubled to 2RH or 2HR. It doesn't really matter on the order of that. And then the h gets squared. That you're going to do a lot in the next chapter. And then you can distribute this -4 plus 3. And it always turns out on ones like this that you get these 6 terms and none of them are like terms. So this is the full answer to this part only. It looks long, messy, and complicated, but it comes out nicely later. This is teaching you one step of the process. So r squared plus 2RH plus h squared minus 4r minus 4h plus 3. This is the algebra side to a major calculus concept, part of it anyway. Here, and this is even more of it. So what you just did was part A on the last problem. And then there's a part B and a part C. All three of these parts are algebra. Then there's a part D that they're not doing here because they can't have you do that part till chapter 3. There's a part D that's the easiest part of them all that a junior high kid could do. But the problem is a junior high kid would never get past part A, B, or C, actually. So there's 3 algebra steps that are messy, and then there's a real easy calculus step that they're not doing on this problem that a junior high kid could do. It's actually more common to do x plus h. This one had r plus h, but it's usually x plus h. So my original f of x is 2x squared minus 5x plus 7. First, we do exactly like problem number 14. Everywhere there's an x, put an x plus h. This part's going to be the same as problem number 14. There's just an extra 2 right here. So let me do this part here first. This is always the same. You get x squared. You get your 2xh for these two. 2xh or hx, however you want to write that. And then you get your h squared. That's how you square that binomial every time. And that's all we had on number 14. But here on 15, then you have to distribute this 2 to all 3 of these parts. So in the part A answer, there's 6 terms. The first 3 terms are 2x squared plus 4xh plus 2h squared. And then this is the same as number 14, minus 5x minus 5h plus 7. So this was very similar to problem number 14. We just had an extra 2 to distribute into part of it. That's part A. A junior high kid could never do that probably, unless they were like a young Sheldon. So 2x squared plus 4xh plus 2h squared minus 5x minus 5h plus 7. Part A was just like number 14. So it turns out the next two parts are actually easier. The hardest part is part A. So next what happens is you take that answer you just got and you subtract the original f of x, which is always given to you. So I'm going to just tack on this minus the original. So I just cheated a little and didn't write it down, but I'm going to write it down now. There's a 2x squared. There's a 4xh. There's a 2h squared minus 5x minus 5h plus 7. That's those 6 terms that are all different. Then what happens is you're going to distribute this negative, and two things happen. First, notice that there's 3 terms right here. There could be 1, 2, or 3, or however many. This one happens to have 3. When I distribute the negative in, all it does is switch their signs. So this positive 2x squared right here is going to switch to negative 2x squared. And here's the part that makes this easy. This always cancels with something out of this big mess. If you don't have something in here that it cancels with, you did something wrong in part A. So you're going to know if your part A answer is right. I mean, here you know it's right because they said it was. But if you were doing this on a test where you have to do all 3 parts without being able to check your answer each time, that's your double check. Those always cancel out. In fact, all the terms here cancel out after you switch them. So the negative 5x is going to switch to positive 5x. The double negative will switch it to positive. But then there better be a negative 5x here somewhere. Yep, that cancels it. And this positive 7 will turn into a negative 7 and cancel out the positive 7. That always happens. If all these terms don't all cancel out over here, you did something wrong. So part B, all that you have left are these 3 terms that I'm circling right now. And one thing to notice about this is, notice they all have an h in them. So what's left is 4xh plus 2h squared minus 5h. You can cheat a little bit and look up here in part A. Anything with an h in it is going to be there, and anything without an h is going to go away. That's the double check. If that doesn't, make sure don't just assume it's going to happen, because if you just assume it'll happen, you might have made a mistake in part A, and that's your way to catch a mistake in part A. Then part C is easy too, because part C, all you're going to do is take what you have left and literally divide by h. So you don't have to get the greatest common factor off the top. All you need to do is factor out an h off the top. Every term has at least one h, so you can take an h out. There would be a 4x left over right there. This one of the 2 h's would go away, but there would still be a 2h there. And then out of the minus 5h, the h goes away and the minus 5's left. Out of the 3 remaining terms, take an h away from each one out front. Once it's out front, then it can cancel with the denominator. So this is the part C answer. 4x plus 2h minus 5. It turns out this divided by h causes a big problem in what we're trying to do in calculus. So the whole goal of this big mess is to get rid of that bottom h. It doesn't go away till the very end. Once it goes away, then things get easy. So you'll see that in the next chapter. So we just went from a long, hard problem to a very easy one. This is just vertical line test. Determine if the graph is a function. That's always determined by the vertical line test. Can we touch this vertically twice anywhere? No. Parabolas are functions if they're right side up or upside down. So this is a function. The problems are in order. This was two problems ago was problem number 57 in the textbook. That one took 15 minutes to do one problem. Then number 61, what's normally the higher the number, the harder the problem gets. And then here was an extremely easy one somehow. Now, here's the same kind of deal, except it's not just a yes or a no. This is not a function. A circle is not a function. It's failing the vertical line test everywhere you go. And all you need to do is fail it one time. So decide whether this graph is a function. No, it's not. It's definitely no, which is A or B. Because a vertical line can be drawn that intersects the graph more than once. Yep. It's about a vertical line. It's not about a horizontal line. Okay, even, odd, or neither. It's not necessarily whether there's an odd exponent in it. But if it is an odd exponent, then the answer definitely will not be even. You can eliminate that. But just because you have odd exponents doesn't mean the answer is odd. It could still be neither. Here's how you really do problems like this. If I have 6x to the third, what you do is you plug negative x in for any x's that you have. That's the first step. Plug in negative x. Then simplify what you have. If it goes back to what you originally had, then it's an even function. If you go exactly back to the original, it's even. If it's exactly the opposite, if all the signs are opposite of the numbers, then it's odd. If some go to the same and some are opposite, then it's neither. So when you have a negative to an odd power, and negative to an odd power makes the whole thing negative. So it doesn't change what you have here. It's not going to change the 6 or the x or even the 3. It's all about, is it positive 6x to the third or negative 6x to the third? A negative or an odd to a negative is negative, and this is positive, so a positive times a negative is negative. This would simplify to negative 6x to the third, which is the opposite of positive 6x to the third. So if you get an opposite result, the answer is odd. So for example, say you had 6x squared plus 4, and you plug negative x in anywhere there's an x. Well, a negative to an even power switches to positive. And then this is positive, so the front term is going to go back to 6x squared, which is the same as the original. And the 4 doesn't even have an x, so that's not going to change. So the first term is the same, the second term is the same, every term is the same as the original. This is an even function. And you probably would guess that it was even because it had an even exponent at the beginning. So if there can be more than one exponent, I could give you a 6x to the fourth and a 3x squared, and then there can be more than one x. You just have to take these term by term. If the problem has only even exponents or only odd exponents, you can eliminate the other one. Only even exponents means odd can't be an answer. Only odd exponents means that evens can't be an answer. But just because you have even or odd exponents doesn't guarantee an answer. Here's why. Say you have 6x to the third plus 5x minus 7. If you give this to students, they assume the answer is odd to this one, and it's not. It's definitely not even either. It's definitely not even because I have odd exponents. There's a 3 here and there's a 1 here. You can immediately eliminate even. But it's not odd just because those exponents are odd. The only way to tell for sure is plug negative x in everywhere there's an x. And if it's going to be odd, every term has to switch to the opposite as it was originally. Well, this 3 will make this negative stay negative in essence. This negative times this positive 6 means you're going to get a negative for that whole term. It's negative 6x to the third now, and that's the opposite of what it was originally. And that's what we did in problem 18 anyway. Here we have, there is the exponent of 1 can be ignored, so this is a positive times a negative. That's negative. And that's the opposite of the original. So far it is an odd function. But negative 7 doesn't have an x. There's no way to change it in any way. It's going to stay negative 7. It's the same as the original. That's no good. Every term has to be the same to be even. Every term has to be the opposite to be odd. If you have some the same and some opposite, then it's automatically neither. This would be a function that's neither. And another thing about even and odd functions is odd functions are symmetrical to the origin. They have origin symmetry. Even functions are symmetrical to the y-axis. And if you're symmetrical to the x or you're not symmetrical to anything, then you're neither. So this minus 7, what that does to a graph is it shifts it down 7. And then you definitely lose the ability to be symmetrical to the origin when that happens. You could potentially still be symmetrical to the y-axis, but not with odd exponents. So this one was odd, but I just covered all 3 possible cases. Oh no, here's another one. Okay, so even, odd, or neither. I've got an even exponent. I got an odd exponent. Now maybe we should look at this graph a little closer because there's no obvious answer that would be sticking out. Maybe you're guessing neither because there's one exponent that's odd and one that's even. But actually what this is a rational function from algebra. The denominator factors into x plus 3 and x minus 3. It's got 2 vertical asymptotes, negative 3 and positive 3. And if the degree of the bottom is bigger than the degree of the top, then it's got a y equals 0 horizontal asymptote. If I plug 0 in for x, that would give me the y-intercept. And the top would be 0 and the bottom would not be. So 0 divided by anything is 0. It goes through the origin, actually. And then I could plug in some other numbers, like say you plugged in 4. Plug in 4. 3 times 4 is 12. 4 squared is 16, minus 9 is 7. 12 divided by 7 is positive. So when x is 4, the y is positive something. So this is probably going to curve like so. And then if I plugged in negative 4 over here, the top would be negative 12, but the bottom would still be 7. So that would be probably something like this. So it's definitely not symmetrical to the y-axis. If this curve was here, I would need a curve here to be symmetrical to the y-axis. It is symmetrical to the origin so far. So another question might be, what's happening in the middle? Sometimes with these problems, the middle goes like this. Because what tends to happen is this tends to be the opposite of that, but sometimes they both go in the same directions. So we could play with this some more to see the graph, but this problem, and what if you did f of negative x on this too is another thing. The only issue is I don't have too many exponents to work with, but this would be 3 times negative x over negative x squared minus 9. The bottom is definitely going to go back to the way it was originally, x squared minus 9, but the top is not the same as it was originally. It's negative 3x. Now, and I don't have the term by term to look at to say every term is the same or every term is the opposite. So this could just be a case of if you could get a better idea of the graph, which might take a while to graph it, because you'd have to try like negative 2 and negative 1 and positive 1 and positive 2. You could try more x's as needed. Let me just quickly sketch it in a calculator and see what it looks like, because that would give me a better idea quickly. If I graph it in, let me change this. Windows, what I'm looking for. Okay. Oh, I know I want. Here we go. I got to turn this off is what's wrong. There we go. Off, okay. Here we go. Okay, so the graph is, yeah, it's doing exactly what I thought it would do. So that trick about the f of negative x, that's only going to work if you have a polynomial. This graph is what I suspected. It's got the curve in the downward left-hand part. The middle kind of looks like a x cubed graph. And then the far right is opposite of this one. And this is symmetrical to the origin. So this would be an odd function because of the graph. The graph will tell you if it's symmetrical to the origin or to the y-axis. That's a way to tell if it's even, odd, or neither. The f of negative x idea, plugging negative x in, that only works on polynomials. So it didn't help here to do that. So this is an odd function because it's symmetrical to the origin. And the f of negative x wouldn't have told me that. Okay, finally, here's our last problem. We got the price of silver. S of t is the average price in dollars per ounce. Is S of t a linear function? No, linear needs to be straight. This thing's curvy. It's definitely not linear. It increases and it decreases. So linear functions either increase or they decrease, not both. What is the independent variable? The independent is always the x, so that would be the year right there. Year is independent. Dependent is always the y, which is dollars per ounce right there on the graph. Dollars per ounce are just dollars. So it's not that x is always, oh, did I? Yeah, see, it is dollars per ounce. So that is average price. It isn't just dollars. It's, see, they tricked me. It's average price because per ounce makes it an average instead of just dollars. It's not just dollars, it's dollars per ounce. That's an average. They even said it was average up here. I just got lazy and didn't read it. Okay, the domain, you can see that from the graph. The farthest to the left it goes is the year 2000. The farthest to the right is... I guess that would be 2010, 2011, 2012, 2013. So it goes from 2000 to 2013. Estimate the range. Yeah, that's hard to tell. The lowest it goes, well, maybe it's, the lowest it goes is 5, almost certainly 5 right there. The highest is this point, which seems to be a little higher than 45. Is that enough to say 46? I'm not sure. Maybe that's why they want interval, or that's why they want an estimate. So I'm going to try 5 and 46 first and see if they take that. It's clearly a little higher than 45. Maybe it's not even 45 and a half. It's hard to tell, even if you blow this up. So is 46 too high? I'm not sure. I guess that is too high. And it could be that they're just rounding to the integer, or maybe they want me to put 45 point something. It's hard to tell. So sometimes you don't know until you get these wrong. Okay, so I guess they're arguing that that's closer to 45 than 46, but it would have helped if they would have given me more spots on the graph to tell where 46 is. It was clearly higher than 45, but I guess it's not that much higher than 45. What was the average price per ounce in 2007? See, the 2007, that's the domain, and the average price is the range. So this is what you do, is you plug in a domain and you get an answer spit out as the range. 2007 would be halfway between 2006 and 2008. Go up till you touch the graph. Luckily, it looks like it's exactly on 25. And then we got to be careful. Dollars per ounce. Okay, so I guess they just want $25. Sometimes you have to worry about units. In what year was the average price $45 per ounce? So this is backwards. Now they're giving me the Y and they want the year, which is normally the X. So go to 45. See, I guess since that's that 2011, that was the highest point of the range too. So 2011 is when it reached its highest in this graph. Okay, so I've done examples of all 20 problems. If you click here, you can see I got green checks on everything except 11, and the only reason I didn't get 11 fully correct was I missed it on purpose last time. And if I currently have a 98.3, if you're satisfied with that, that's fine. You don't have to redo number 11. If it bothers you not to have 100, the good thing is you can hit similar question and do it again. And it's also not a bad idea if you missed a problem or don't understand one, or you did it 3 times so you finally got it right, that you might want to come back and do it. You can do one that's already correct over again. Let me go back to that easy one. What was it, 16? I can just hit similar question even when it's correct. Now it gives me exactly the same thing, so the answer is still yes. But if I do it more than once, similar question, you can do problems over and over again, whether they're right or wrong, as much as you want until the deadline. So until September 23rd, you can keep working on these. What if I get this one intentionally wrong? Final check. No, so now it says I can either save my best score and I'll keep my 98, or I could punish myself and save this attempt. And now I just lost 4.5 points. But even if that happens, I can hit similar and get it right the next time. And now I'm back up to 98. Or if you get it wrong, just make sure you don't punish yourself. Save best score, and then you'll stay at 98 as well. So that's as good as you can. Play with these as much as you need. There's this help me solve this, view an example, get more help. Ask My Instructor sends me an email so I can help you on the question you're on. So there's a good example of a set of homework. We did all the problems in section 2.1. The next video will have problems from 2.2. So work on 2.1. And you can use this video to pause and rewind and go back as needed as you're working on section 2.1. And I'll see you next time for section 2.2.